A patch of ground in Wyoming is swelling upwards. Right now, today, scientists are watching it happen in real time, measuring its rise in fractions of an inch, holding a planet's breath. This isn't just any piece of land. It's the northern rim of the Yellowstone caldera, the planet's largest active supervolcano. And the last time this specific area swelled like this, the system erupted. Not with ash that blackens continents, not a fiery apocalypse, something faster, something more immediate, and something that is happening again. On June 13, 2026, a fissure 61 feet long tore open the earth nearby, vomiting boiling water and turning a pristine river a ghostly milky gray. It was not a super-eruption, but it was an eruption, and it proves the clickbait headlines are hiding a more complicated and immediate truth. The danger at Yellowstone isn't just some million-year time bomb, it's a pressure cooker blowing its lid, right now, in small, violent bursts. So what is really happening under Yellowstone? What do you think is driving this new surge of activity? Let me know in the comments below. Let's begin. A huge number of people watch these stories unfold and completely forget to subscribe. If this is the kind of detail you can't find anywhere else, take 1 second and hit that button. The story of this volcano is changing month by month, and it's the only way to guarantee you won't miss what happens next. It is an emergency, and it's vital you subscribe to stay informed. Yellowstone breathes. Before we can understand the fissures and the explosions, we have to understand that simple, unsettling fact. Using a network of hypersensitive GPS stations scattered across the park, scientists like Michael Poland, the scientist in charge of the Yellowstone Volcano Observatory, can watch the entire caldera floor rise and fall by inches every single year. It inhales, and the ground swells upwards. It exhales, and the ground subsides. This isn't theory. It's measured, documented reality. The process is called deformation, and it's the vital sign of a living volcano. The movement is driven by a chaotic, unknowable world miles beneath the surface. Sometimes it's a pulse of new magma, arriving deep in the reservoir. Sometimes it's the movement of superheated hydrothermal fluids, a massive underground plumbing system of water hot enough to melt lead. Sometimes it's just the ground settling as those deep fluids cool and contract. For most of the last 100 years, the general trend has been up. The center of the Yellowstone caldera, a vast 28 by 53 mile depression left by an ancient cataclysm, has risen by nearly 3 feet since measurements began. That's not a uniform steady lift. It happens in fits and starts, in different places at different times. Two enormous sections inside the caldera, known as the Sour Creek and Mallard Lake resurgent domes, act like geological lungs. These are not small hills. They are massive, uplifted regions of the caldera floor, each miles across, pushed up from below by the pressure of the magma chamber. For decades, scientists tracked their movement using painstaking land surveys. A retired USGS pioneer named Daniel Dzurison spent much of his 43-year career doing just that, running leveling lines across the park to measure every subtle shift. His work, decades before GPS made it easy, proved the ground was alive. From the mid-1970s until 1985, the whole caldera was swelling upwards, at about an inch per year. Then, suddenly, it reversed. It began to sink, a long, slow exhalation that lasted for a decade. Then in 1995, it started rising again. Inhale, exhale. The average rate is just 1 to 2 inches per year. Barely perceptible. It's a rhythm the volcano has followed for centuries. But starting in 2015, the overall caldera began a prolonged period of subsidence. A long exhale. Things seem to be calming down. And that's what makes the events of July 2025 so significant. Because while the rest of the caldera was still sinking, one specific spot on the northern rim woke up. A zone geologists had been watching for 30 years. A place they called the Norris Uplift Anomaly. And it started pushing upwards again, alone. This is an incredible system of unimaginable power. What's the most surprising thing you've learned about Yellowstone so far? Drop it in the comments below. The Norris Uplift Anomaly isn't just a place. It's a character in this story. A recurring troublemaker. It first announced itself in 1996. While the rest of the caldera was doing its slow dance, this zone just outside the main caldera rim, centered near the Norris Geyser Basin, started to swell on its own schedule. Between 1996 and 2004, it bulged upwards by almost 5 inches. A localized pocket of intense pressure. Geophysicists theorized the cause was a small blob of magma accumulating deep beneath the surface, around 9 miles down. Not a sign of an impending super-eruption, but a distinct pulse of energy into the system's upper levels. It was a geologic mystery unfolding in slow motion. And then, as abruptly as it started, it stopped. The uplift ceased in 2004, and the area entered a long period of slow subsidence, deflating like a spent balloon. But the energy it injected had consequences. The Norris Geyser Basin is one of the hottest, most dynamic, and most acidic thermal areas in all of Yellowstone. It's a landscape of roaring fumaroles, acid-bleached ground, and unpredictable geysers. It is, in effect, the volcano's exhaust pipe, and the uplift changed its behavior. Steamboat Geyser, the world's tallest active geyser, had been mostly quiet for years. Then in March 2018, it roared back to life. It began a cycle of spectacular, powerful eruptions, hurling water over 300 feet into the air. Between 2018 and 2025, it would erupt a staggering 177 times. Scientists believe this reawakening was a delayed reaction to the ground deformation, the shifting and stressing of the underground plumbing system. The uplift had squeezed the rock, changing the pathways for water and steam. A decade later, Steamboat responded. The system was remembering that pulse of energy from 1996. Then, in July 2025, it happened again. The GPS stations at Norris detected a new, unmistakable trend. The same patch of ground that had swelled and stopped was now swelling again. The anomaly was back. The exhale was over. A new inhalation had begun. This time, the system didn't wait a decade to respond. In November 2025, a swarm of small earthquakes rattled the ground directly beneath the center of the new uplift. The ground was shifting, cracking under the renewed strain. Then in February 2026, another geyser in Norris woke up. Geyser, a fan favorite known for its large, clockwork-like eruptions, had been quiet since 2020. Suddenly, it was erupting again. The swelling ground was directly and immediately changing the behavior of the geysers on the surface. This wasn't a forecast. It wasn't a model. It was cause and effect, playing out in real time. The same ground was rising, and the last time it rose, the geysers reawakened, the plumbing shifted, and the park's most dangerous, unpredictable eruptions became more frequent. The system was priming itself. If the story of this reawakening shocked you, hit the like button, and if you have family or friends who only know Yellowstone for old faithful and gentle trails, share this with them. They need to see the volcano's other, more violent side. To understand what comes next, you have to stop thinking about a mountain of lava. You have to start thinking about a pressure cooker. The real, present-day danger at Yellowstone isn't magma breaching the surface. It's water. The ground beneath the thermal basins is a labyrinth of fractures and conduits. Water from rain and snow percolates deep down, where it's heated by the immense energy of the magma chamber far below. It reaches temperatures well above the surface boiling point, but the immense pressure of the overlying rock keeps it in a liquid state. It becomes superheated. As this superheated water flows upwards, it dissolves silica and other minerals from the surrounding rock. When it nears the surface and cools slightly, those minerals precipitate out, forming a hard, concrete-like seal. They create a capstone, trapping the intensely hot, pressurized water beneath. This is where the danger builds. Pressure, heat, and steam accumulate behind that mineral seal. The system becomes a natural, geological bomb. All it needs is a trigger. A trigger can be a small earthquake, fracturing the seal, or it can simply be the pressure building to a point where the seal can no longer hold. When that seal breaks, the pressure overhead vanishes in an instant. The superheated water, no longer held in a liquid state, flashes violently and instantaneously into steam. Water expands to 1,700 times its original volume when it becomes steam. This explosive expansion is a hydrothermal eruption. It's a ground-rupturing blast of steam, boiling water, mud, and rock, hurled hundreds of feet in every direction. It doesn't produce ash clouds or lava flows. It creates craters. It destroys everything in its immediate vicinity with the force of a buried explosive. It happened on September 5, 1989. For years, a small feature in the Norris Back Basin, called Porkchop Geyser, was just a placid, rolling hot spring. Then in 1985, it changed. It began roaring, a continuous jet of steam and water so loud it could be heard a mile away. The ground around it was trembling. For 4 years, it seethed with this newfound energy. Then, on a clear September morning, it exploded. Without warning, Porkchop Geyser detonated. It hurled rocks, some the size of small appliances, over 200 feet away. The blast completely obliterated the geyser's cone and left behind a jagged, steaming crater. Thankfully, the basin was empty of tourists at the moment of the blast. After the explosion, Porkchop was gone. In its place was a simmering, murky pool. The pressure cooker had reset itself. The story of Porkchop Geyser is the crucial precedent. It's definitive proof that these thermal features are not stable tourist attractions. They are unpredictable, dangerous, and can transform from a gentle spring to a violent explosion with little to no warning. It was a historical footnote for decades, until 2024, when the same thing started happening again. The focus of Yellowstone's modern instability isn't at Norris. It's miles away, in a place called Biscuit Basin. It's a smaller, less visited thermal area, a delicate landscape of blue pools and small, quietly simmering geysers. Or, at least, it was. On July 23, 2024, a massive hydrothermal explosion occurred at a feature known as Black Diamond Pool. For years, it had been a deep, dark, placid spring. But that summer, it erupted with ferocious power. The blast was powerful enough to destroy a section of the park's boardwalk, tossing splintered planks like matchsticks. It threw rocks and debris hundreds of feet, littering the surrounding area with evidence of its violence. The National Park Service immediately closed the area. Scientists from the YVO descended on the scene, finding a transformed landscape. Black Diamond Pool was now a churning, muddy, agitated cauldron. The pressure cooker had blown its top. The area remained dangerously unstable. For the next 2 years, Biscuit Basin was a geologic hot zone. The ground trembled with small tremors. The temperature and chemistry of the water in the surrounding pools fluctuated wildly. The system was clearly not done. The explosion at Black Diamond Pool was not an ending. It was a beginning. On June 13, 2026, the other shoe dropped. Early that morning, seismic and acoustic sensors near Biscuit Basin detected a strange signal. A low-frequency tremor, the signature of fluid moving violently underground. Park rangers and YVO scientists knew something was happening. Just north of the now infamous Black Diamond Pool, the ground gave way. Another hydrothermal explosion, more powerful this time, didn't just create a crater. It tore the earth apart. It opened a fissure 61 feet long and 5 feet wide. A raw gash in the ground, filled with boiling water measured at 194 degrees Fahrenheit, near the boiling point for that high elevation. Steam billowed from the wound in the earth. This new fissure drained a massive volume of superheated, mineral-rich water, which flowed directly into the nearby Firehole River. The river, normally a crystal-clear waterway famed for its trout fishing, turned a morbid, milky gray as a plume of silica and sediment choked its flow for miles downstream. This wasn't a distant geological event. This was an active, ongoing environmental disruption. The explosion and the fissure are direct physical proof of the instability brewing beneath Yellowstone. Michael Poland of the USGS is clear. Yellowstone is a dynamic geologic system. The one constant is change. He also notes that before any truly hazardous magmatic activity, the rates of ground deformation would need to accelerate dramatically, far beyond the few inches per year currently being observed at Norris. But he also confirms that these hydrothermal events are the park's most tangible, immediate hazard. What happened in Biscuit Basin in 2024 and 2026 wasn't a warning about a potential super-eruption in 10,000 years. It was the hazard itself. The eruption isn't coming. It's here, just not in the form anyone expected. I know, I'm asking again. But our analytics tell me a lot of you value this deep dive, and then the video ends and life happens. Take 1 second, it's free, and it tells the algorithm that stories this important, based on real science, deserve to be seen by more people. Your subscription is a vote for quality. Thank you. So if the immediate threat is steam, why is everyone so afraid of lava? Because of what happened 640,000 years ago. That was the eruption of the Lava Creek Tuff, an apocalyptic explosion that ejected 240 cubic miles of rock, dust, and ash into the atmosphere. It was a blast 1,000 times more powerful than the 1980 eruption of Mount St. Helens. The ash covered half of North America. The ground collapsed, forming the massive 45 by 85 kilometer caldera we see today. That event, and two other, even larger ones before it, the Mesa Falls Tuff 1.3 million years ago, and the colossal Huckleberry Ridge Tuff 2.1 million years ago, are burned into our collective psyche. They are the reason the word Yellowstone is synonymous with super-eruption. Seismic imaging of the magma chamber today reveals a very different picture from the pop culture image of a giant cavern of molten rock. The chamber is mostly a solid crystalline mush, a sponge-like body of rock with magma filling the gaps. It is not a liquid pool ready to explode. For magma to erupt, it needs to be mobile. This typically happens when a new injection of much hotter magma from deeper in the mantle rises into the system, remelting the crystalline mush and increasing pressure. That process takes time, and it would leave unmistakable clues. The ground would swell not by inches per year, but by feet, or even yards, per week. The number of earthquakes would skyrocket from the typical 1,500 to 2,500 per year into the tens of thousands, and they would get stronger. The chemistry of the gases escaping from fumaroles would change dramatically. We are not seeing any of that. But what if magma did find a way to the surface? Would it be the end of the world? History tells us, probably not. The last time true magma, not steam, not water, but molten rock, breached the surface in Yellowstone was approximately 70,000 years ago. This wasn't an explosion. It was a quiet, relentless ooze. The eruption occurred on what is now the Pitchstone Plateau, in the southwest corner of the park. It wasn't a sky-blackening ash cloud. It was a thick, viscous flow of rhyolite lava. Rhyolite is so thick it barely flows at all. Imagine a wall of molten glass, hundreds of feet high, creeping across the landscape at the speed of a glacier. It would have incinerated the ancient forests in its path, burying the terrain under a thick blanket of black volcanic rock. It would have been an unstoppable, world-altering event for the local environment. But it would not have been a global catastrophe. This is the most likely scenario for the next magmatic eruption at Yellowstone. Not a super-eruption, but a large, slow-moving lava flow. Still incredibly destructive on a local scale, but not the civilization-ending event of popular imagination. The park actually holds the scars of even larger hydrothermal events. 13,000 years ago, a series of massive steam explosions, far larger than Porkchop or Biscuit Basin, created giant craters in the northern part of the lake. One of these, Mary Bay, is over 1.5 miles across. It is the largest hydrothermal explosion crater known on Earth. The volcano knows how to make big bangs without ever using lava. The ground at Norris is still rising. The new fissure in Biscuit Basin is still steaming. The system is active, and it is changing faster than it has in a decade. The breathing has become heavier. The scientists at the Yellowstone Volcano Observatory are not panicking. They are watching. Every GPS data point, every seismic tremor, every change in gas chemistry is analyzed. They have built one of the most sophisticated volcano monitoring networks on the planet to track a system that defies easy prediction. The return of the Norris Uplift Anomaly, the waking of Steamboat and Aquinas geysers, the violent explosions in Biscuit Basin. These are not isolated incidents. They are connected dots on a map of a restless giant stirring in its sleep. The current activity is not a sign of an impending super-eruption. Mike Poland and his team are firm on this. The data simply isn't there. But that is not the same as saying there is no danger. The danger is the pressure cooker. The danger is a sudden, unannounced explosion of steam and rock in a thermal basin crowded with summer tourists. It is a 61-foot fissure ripping open the ground. It is the proven reality that parts of Yellowstone are becoming more volatile, more aggressive, and more dangerous, right now. The deep threat of a caldera-forming eruption remains a distant, generational concern, a geological probability on a timescale humans can barely comprehend. The immediate threat is happening on our timescale. Weeks, months, years. The question is not if the next hydrothermal eruption will occur. The only questions are where and when. The Norris Uplift could stop tomorrow, or it could accelerate. The plumbing beneath Biscuit Basin could stabilize, or another, larger section could give way. We have drilled into the past, we have measured the present, but the future of the volcano is being written, mile by mile, deep beneath the surface of the park, and all we